Alright, we are welcome back once again. Today we want to discuss, we are continuing on the set operation in topological space. And the last class we try and discuss on the accumulation point and the closure of a set with either with a derived set. And then we all know how we define that. But today, because I want to go into interior, exterior, and boundary of a set. That is interior point, exterior point, and boundary of a set. Now let's start with interior. Now, definition. Now we are talking about interior point. Interior point. Whatever interior point, what does it mean? You're saying that definition now. Let A be a subset of a topological space, a point P in A is called an interior point, of A if P belongs to an open set G contained in A. That is, if you pick P, be an element in G, which is subset of what? Of A. The subset of A, where G is what? Where G is open. Don't forget that G is an open set. But this is a member of the topology. So that is where I can have it what? The interior point. Interior point is called that if you have a point P in A, is called an interior point of A if P belongs to what? The open set G contained in what? In A. That is, when you pick, you have a topology now. You have a topology. You have a G, be a member of that topology now. Then we're saying that for every P that a member of that set A, that means that P must be what? In G, and this G is a sub of what? Of that A, of that set. If that P now referred to as what? The open set. You get it like that. So now let's look at what we need to also understand. Now this is noted by what? The set point. The set of interior points of A is noted what? Is noted by what? Int of A, or we can write what? A raised by what? Sec. So that means by what? That's how you can define your interior point of A. So now, and it's called interior of what? Interior of A. Now we have a proposition that characterizes the interior point. We're saying that we have a position which characterizes that. Our position says that the interior point, the interior of a set A, is the union of all open subset of A. I got that. Also, furthermore, we have what? One, interior is opened, it's an open set. Two, is the largest open subset of A. That is, if G is an open set, I don't know, an open subset of A, open subset of A, then I have G is contained what? Interior of A is contained in A. That is what. Then the third position I have is that A is open. It's open if and only if A is equal to a set of its interior point. That is interior point. That's why I have what we call it what? Exterior of a set. Now, There's something called exterior point. Now, exterior point is just the complement of the interior point. How does that complement? That is, they say that the exterior point of A, the exterior of A, written, you can write that as x of A. How does that now? X of A is the interior complement, is the interior of the complement of A. Complement of what? Of A. That is, you can say that exterior point EST of A is just the interior of what? A complement. But like what we have in that of subspace, I mean the closed set and the open set. So that means the interior point of A written as this is the interior of the complement of A. And the x of A is equal to the interior complement of that set, set A. So the boundary point now, the boundary of A now, we explain the interior point, then the boundary point, the boundary of A. You can say that the boundary of A, that is the boundary of A, the boundary of A, that is written as you can be noted by this B of A. That is the boundary of A is the set of points, is the set of points which do not belongs to interior or exterior of A. So that is the set that not belongs to interior or exterior point of A. If that as what? The boundary of A, boundary set of a point, boundary set of A. So that is what we can talk about the interior point. Now, there's now a theorem that connects the closure property, interior, and the boundary of a point. And the theorem is this. It says we have a result, a theorem here. And so it says that let A be any subset of a topological space. What's that? Be a topological space now. Let's say topological space X. Then the closure of A, is the union of interior and what? And the boundary of A. That is, you can say the interior is equal to what? Interior of A, boundary of A. Or you can write as what? A of this, what? B of A. So that is giving us what? This gives us a closure. That is, you can write the closure as the union of what? Interior point and that of the boundary point. Now, let's look at the example of how we can actually determine the interior point, exterior point, and boundary point, given a particular topology now. So let's look at that now. So that will give us an example on how you can actually obtain the result. Now, look at this example. Look at the example now. Very, very simple and basic. Look at this example. Look at this example now. Look at this example. We are given that consider the topology. Consider the topology. Let's say we are given a topology tau, we go as what? X, empty set, we have set A, C, D, A, C, D. Then we have B, C, D, E. Now we are doing this topology now on X. And X is what? A, B, C, D, E. I got that now. And we are doing a subset. And a subset. A, this gives us to be, let's say, B, C, D of X. Now, what are the exterior points of this set? Now, let's go back interior points. What are the interior points? Interior point is defined as it's a set of P in G and A is a subset of. Don't forget that your G is in what? Is in town. Abi? Now let's start from B. Let's start from B. If you look at B, what are those open sets that contain B? Let's start from there. That contain B. We are consider B now. We want to check whether B is an interior point. Now, if you consider B, what are those elements open sets that contain B here? Which are also a sub of A. If you look at this now, X not. Now BC here. Okay, no, B cannot be interior point because there is no. The only point that contains B is this. And we have the point that contains B is here. No, B is B, C, D, E. I mean, B is also in X also. But is B, C, D, E the sub of what? Is it a sub of A? Is it a sub of A? No, it's not. This is not a sub of A. So B cannot be an interior point because there is no sub of open set that contain in A. But let's consider C. Let's consider C now. Open set that contains C. Open set that contains C. They are what? Let's check it. We have A, C, D. Abi. Then what again? C, D. Can you see that? Then we have what? B, C, D, E. Now, by the time you look at this, then we have X also. But look at all this set of open sets that we have. From this open set, which one of them is contained in A? You can see that only CD, C, D is contained in what? Is contained in A. Only CD is contained in because you have what? Only CD is contained in because CD says CD is a subset of A. So which implies that based on this definition, I saw that this implies that C is it belongs to what? An interior set now. That is C, that is implies C is what? Is an interior point. Also, the same thing goes for D. Also, D is what? Is an interior point because we can obtain those subset of it are contained in that A. So in this pattern now, so our interior set is now what? Set of A. They are the set of what? C, D. C, D. That is how you obtain the interior point of that set. I hope you get it now. Now, what do you get about the exterior point now? Exterior point of A is what? Interior of A complement. I got that. So let's find the A complement now. I said A is given as what? B, C, D. So this implies A complement now will now give us what? A complement give us A, E. Can you see that? A complement give us what? A, E. So let's find the interior of this complement now. What will be interior of? We are looking for the interior of A, E. What will be the interior point of A, E? Now when you look at it, let's look for a set A. There is open set in this place that is contained. So we are looking for G. That is, if you are considering A now, we are looking for A must be in G, which must be what? A sub of A. Now, let's check where A belongs to the set here now. We can see that our subset of A interior must subset of A complement. Now, when you look at it, we have A. A is in what? A is in A. Because that A is in A, and which is what? A sub of what? A complement. Have you got that? This implies that A interior of A complement is set of A. So there is no other one that's also opposite that contain in A complement. There's no other one. So the exterior point now, the exterior of A is equal to what? Is equal to this set A. So that is what we call the exterior point of that set A. Now, what is now the boundary point? We say that the boundary point is a point. Boundary point of A is a point that does not belong to interior point and exterior point. So what are those points now? The interior set, interior of A is C, D. Interior of A is A and B. So what are the 2 points that does not belong to? That is, you're now going to find that the point that no, then look at when you look at interior, that is you are looking for interior of A union exterior of A complement. Are you getting that now? So and that will give us those points will give us what? You know, this place give us something like A C D. And when it comes to A C D, we have B E. So in a nutshell, our boundary points now, our boundary, the boundary of A consists of what? B consists of A, B of A will consist of what? B, comma E. So that is your boundary point of that. So that's how you can actually determine the boundary and exterior points. You can also obtain the what? Interior point, exterior point, and boundary of the set A. And boundary of the set A. Now, you know there was a theorem I stated earlier. So let's prove a particular result here. Let's prove a particular result here before we proceed. So now, let's look at this result here. Okay, before we go to that, look at this question. It said consider. Look at this example. Consider the topology, the following topology on X that gives us A, B, C, D, E. Now we are considering this one now, and you are given a topology as this: X, comma, empty set. Set A, we have AB, we have AC, D, we have A, B, C, D, and lastly we have A, B, E. So you are given this topology now. You now say one, find the interior points of the subset A. Which give us what? A, B, C of X. Then 2, find the exterior point. Find the exterior point. Exterior point of A. Then third one, find the boundary point of A. Find the boundary point of A. So these are the one question that I have given to us. So what will be the interior point? Solution now. Solution. No, we are doing a topology again. And for interior point to obtain interior point, we are saying that for interior point now. For interior point, we are going to have something like a P in what? In G, which is sub of what? Of that subset A. So when you look at it for A, is A interior point of the subset of this A? Let's check it out. What are those things that are sub of this A now? That contains A. We have A. We have opposite G. The G's are what? We have A is also contained here. We have AB. It's also contained there. Abi. We have ACD. Is ACD contained here? No. So we only have these 2 points, which implies that our A is in what? Is in A, which is a sub of A. Likewise, A is in A, is in what? A, B, which is also a sub of A. Therefore, interior is what? A is an interior point. It's an interior. Is an interior point. Are you getting that? So that's so that A is what? Is an interior point. We can say that A is an interior point. Then likewise B is also the same goes for B, because B is also contained there. So also B is in what? A comma B, which is sum of what? Of A. So which implies B is also an interior point. Interior point. So the not set our set of interior point of A now. Interior of A will be a set of what? A comma B. A comma B. So those are the way you can actually obtain that. Now, what will be the exterior point? Exterior point is the interior. And we all know that exterior of A is the interior of A complement. Abi? Now, what's A complement? Our A complement is just this. ABC. That means we have DE. Can you see that? So now when you have DE here, so we need to find interior of this one. Are you getting that? So to get interior, let's go for D. Let's go at those one that contain D, which also remember of that one. What do you have? We just say a sub of this. What do you have? D. No, we don't have, because A comma D is not a sub of what? A comma is not a sub of A. Are you getting that now? So therefore, the interior point of this is what? Is empty set. That means your exterior of A is what? Is an empty set. So if the exterior of A is an empty set, then there is no what? That is, this implies that there is no exterior point. Exterior what? Exterior point. There is no exterior point there, because none of it satisfy the required condition. So now, what are those ones that does not contain interior and exterior points? They are boundary points. So our boundary points, boundary of A, will just give us B of A. Those points that is not a member of interior point also is not a member of exterior point. What are those points? We have C, D, and what? And E. So that is how you can actually find the interior point and exterior point. So I hope that one is clear to us now. So thank you. So let's look at a result here, another result here, so that we can see how those things have been explained earlier. Now look at this story. Let's check it out. Okay, let's check this out. Look at this result. They said, now let's look at this one also. They said the question says that the interior, the end calculation that I've stated earlier. Let's put the equation now. They said the interior of a set A is the union of all open subsets of A. Furthermore, we have what? 1, interior of A is opened. 2, interior of A is the largest open subset of A. That is, when you are picking G a sub of what? A, this one sub of A. And thirdly, we have A is open if and only if A is equal to what? Its interior point. So those are the things. Now what we do is just very simple. We make a suggestion. Let you have this GI be the class of all open subset of what? Of A. So if X belongs to a exterior point, now I got that, then X belongs to open set G. I believe this is subset of A. Because an interior point now, there is a point that is, there exists, let's say you have I naught such that S belongs to G I naught. So that is for each of them. S is such that S belongs to a union of that I of A of G I. That is all the union of I meaning omega of G I. Then and so A not a sub of what? Union of what? I in this arbitrary of G I. I got that. So on the other hand, if Y belongs to U of I in this one of Gi, I got that. Then you can say that Y belongs to Gi naught. I got that for some what? For some high naught. I got that. So which implies that Y will now belongs to what? Interior point. And then union of I of this omega of Gi also it's also a sub of the interior of A. I got that. So which implies that interior of A is equal to union of actual union of this one of Gi. So that means it belongs to this one. So from here, we can now begin to refer that one. If A not God, we say that it's union of open subset. That one is true, I mean. So by what we just explained here now, we can say that one, A, interior of A is equal to what? Union of I and what? Omega of what? Gi. I got that. Since it's what? It's opened. It's open. I got that. Since it is it is the union of open set. It is the union of open set. So that means open because not all open set now. Definitely the interior of also it also be an open set. The second one is that the second one we want to show that interior of A is the largest open subset of A. So if G is open, if G is an open set, if G is an open set now, I got that of A, then we can now have that G belongs to what? Arbitrary of Gi. I what? In that omega. I got that. So we now obtain union of I in this one of Gi. I mean that means so we can say that G. So we can say that G is a sub of this. I got that, which is give us what? A interior, which is also a sub of that A. I see that. So the third one is like we are saying that if A is open now. If A is open, then notice an open set now. Then I can say that my A is containing what? A interior is containing A. I got all, which implies what? Which implies A is equal to what? Interior of that A. So if A is open, if this is true also, I got if this is true, then A is open since what? Since the interior of A is also what? Is also an open set. So that is how you can prove the proposition of that result. I hope you get it now. So that's all about that. Now, before I go for today, there's also a remark in the theorem I stated earlier that you can actually show that you relate the boundary point with closure. The closure of the set now. Where this theorem says that, look at this theorem, which says that if you have A is equal to what? Interior of A union boundary point of A. The boundary of A. Interior of A equal to the boundary of A. How do you prove it? It's just like you have, since you can say that X is equal to what? Interior of A, I mean the whole set, union boundary of A, union exterior of A. I got it that you can do that now. So, and we know that interior of A, union boundary of A, complement will give us what? Exterior of A. That's actually true. Because interior of A, union boundary will give us what? Exterior of A back. I got it that. So when you remove the interior set of A and the boundary of A from the whole set, you're going to have what? Exterior of this one. So we need to show, then it is required to show that the closure, the complement of closure of A, I got that now, is equal to exterior of A. So we want to show that if you can determine the closure, you don't know something that interior of A union boundary of A is the closure of that set now. So by the time we can able to establish this one now, we will take the interior of that set A. Now to do that, we can say that let P belongs to what? Exterior of A. I got that. So then there exists an open set G shows that what? Shows that you have because we are talking about interior point now, shows that can have P in G, which is what? A sub of what? Of A complement. Which implies what? By definition, which implies G intersection A is what? Is empty. This is what? Is also is empty. So now, so P is not a limit point. It's not what? A limit point of A. Because it does not pick, because empty set is this one now. But for it to be a limit point, it must not equal to empty set. So because this is an empty set now, you can see that P is not what? It's not a limit point. That is, you can say that P does not belong to what? A derived set of A. Not one set of A. And P is not in that set A. So hence, we can say that P does not belong to what? A, the right set of A, union that A. I got that now, which is, this one is saying as what? The closure of that set now. So that means P does not belong to the closure of that set. So in other words, that means exterior of A is a sub of what? This one, complement. So the next step is I want to show that the complement of the complement of the closure of the set A is also contained in the exterior point of A. So we can now equate the two together to obtain the required result. Now what to do here is this. Now suppose B belongs to the closure of this. I consider that now. Suppose you have this.